today we have Andrea Saltelli presenting to us. It's for all of us, and for me personally, it's a dream come true. Andrea, I've been reading your books, and you're author of series of books on sensitivity analysis, and it's important work for so many scholars in so many different disciplines. And you've been working not only in academia but also in actual policy making, right, in the Research Center for European Commission, and now affiliated with so many universities. We are happy to have you here.
Thanks a lot, Mariia. Too kind,
yes.
Too kind. Okay, what to say? I will, after many years of giving lecture on sensitivity analysis, I decided to follow the advice of Nassim Taleb and to do how it says via negativa, no? How you should not do it rather than how you should do it, because I've seen that there is a lot to say in this direction. So we jump immediately in my talk. Tell me if you can hear me well and you can see the screen well, right?
Everything is perfect. Yes, please proceed.
Okay, so you can find my talk or the PDF of my talk on my website, which is very easy to find because it's the same as my name. I will start with some general concept about mathematical modeling, which I believe will be familiar to most of you, but let's go through them quickly. The idea that modeling is a craft more than a science, and this has been said very clear by relational ecologists, in particular by Robert Rosen, who said that when you have the encoding of a natural or even a man-made system into a formal system through the operation of encoding, in the hope that the decoding will tell you about the system you are modeling, you have different system of causality at play in the natural system and in the formal system. He talks about efficient, causal, and final for the natural system, and formal causality for the formal system, using the category of Aristotle. But the point is that it tries to make it that there is no way, no causality error really going from the natural system to the formal system. So the procedure is not driven by some kind of necessity, which will in any case nail the way you do it. There is a lot of space for how you do it, and this is why Rosen said this is a craft more than a science. And this, opened the discussion of what is a model, the discussion about anticipatory system, which are those who have a model of themselves, and all the literature related to this discussion. Naomi Oreskes, in a rather old article, argued that models are better to use also the model via negativa rather than via positiva, in the sense that it's better to use them to challenge an existing formulation, because it's very difficult, not to say impossible, to use models to verify a given law or a given set of presupposition, because models are not physical laws, so they don't lend themselves to the classical Popperian approach of testing and refutation, no falsification, because even if we build a model and the model does not agree with the observation, we don't know what went wrong. What was wrong? The way the model was built, there was an error in the model, the data were not the good data, or the algorithm which was used, the discretization. So Naomi says any part or several parts of the model could be wrong, but it is not so easy to understand which one it is. Something I have discovered in my life as a practitioner, that models have little memory. And I found this from a book of philosophy, this description, which refer to the value VAR model, value at risk, which are used by banks to evaluate their portfolios, the risk of their portfolios. And they say, well, even people who produce those models, which are used in a number of legislation, regulation, Basel, whatever, even the people who wrote this model don't remember the assumption which went into it. So that even less the client using those products can understand what goes on into this model, because it was simply forgotten. And then there is the famous all other things being equal used by the economists, now ceteris paribus assumption, which is very often used, for example, in dynamic stochastic general equilibrium models in economics. But the problem is that ceteris are never paribus. I mean, you cannot just modify one variable. I mean, you can, of course, you can take one of these, the SG model, and propagate a shock through the economy, which is interesting to see what a single variable can do. But in real life, when you change one of these variables, I don't know, the price of a commodity or of the salaries of a sector, all the other variables in the economy change as well. So ceteris are never paribus. And in particular, according to the critique of Philip Mirowski, those models rely on two very strong assumptions, which is that the agents will behave rationally and they have perfect information, and that the markets are efficient. You know the joke of two economists walking by a $100 bill on the ground, and they say, oh, don't pick it up, because, you know, if this were a real $100 bill, someone else would have picked it up. So this is, and okay, Mirowski also makes some, the construction of this concept as used in economics. And this is a very nice and much readable book on the topic. One consequence of this DSG story is something quite funny, which happened during the on the onset of the last recession, 2008, the Lehman Brothers failure, is that both the US Senate and the late Queen Elizabeth had embarrassing discussion with their respective economists, asking why the economists hadn't set this down. This is described really very well, with a lot of irony and panache in the book of Mirowski. I just quoted it if you want to look at it. Okay, so this is sensitivity analysis, which we are discussing today. In this highly idealized way, you can plug into the sensitivity analysis everything which may change the inference, and you can propagate all this uncertainty through the model to generate the gray curve on the right-hand side. And this is an uncertainty analysis. Clearly, this is very, you see, this is very optimistic, because assume you're able to put all these together, and then you can decompose the uncertainty in the gray distribution according to the source. Where is this uncertainty coming from? So we have uncertainty and sensitivity analysis. So I will be going through it, as I said, via negativa, also because I noticed that many sensitivity analyses which are published are done in a way which is really not useful, and I will try to make the point in this presentation. So a first recommendation would be to use a method which is appropriate to the problem. Don't use just any method, but a method which can be defended. Imagine that you have to defend your sensitivity analysis before an audit. You must be able to explain why you have selected one method rather than another. This is lead me to introduce now the variance-based method, for which you can use this book, which is now freely available online because it has been hacked by the Russian hackers so it's on LibGen. But if you want, you can read the book on Chinese, because it's been translated into Chinese by a brave scholar of the Academy of Science of China. So this is, in a nutshell, a crash introduction to variance-based measure of sensitivity analysis. Here you have two scatter plot of two different variable for the same output. The output is always on the ordinate axis. The abscissa is variable xi and xj. The points are the same points, only they are sorted once along xi and the second time along xj. And I can also do something like taking a local average of those points. Those are the pink points. so that I do bins of different sizes so that each bins contain the same number of points. And so those average which you see here give you some information about how the function is, how this particular variable is influencing the output. So each point, each ping point is a local average, but you can take the variance of the points to obtain a sensitivity measure, which is just a single number. And of course, in this case, you would say that upper curve flag a variable which is more important and which also has a higher value for this variance of the local mean. So for a model which is additive, you can decompose the total variance of the output as the sum of these partial variances. But this is a bit of a tautology because this is the way additive models are defined. A model is defined as additive when this relation holds. Then you can divide by the global variance and you have a nice number between 0 and 1. So this is a sensitivity index of the first order. And statisticians like this because it's the same as Pearson correlation ratio. In practice, this corresponds to taking the average of the smoothed curve, but is also correlated to the straight line. In this case would be the standard regression coefficient, while the curve would be Pearson correlation ratio, which is normally called eta squared. So SI is identical to eta squared. So this, in this way, you can talk to statistician and they know what you are doing. Of course, there is something also for non-additive model. Here, if we were in a room, I would now ask you if this variable is important. And this is not so immediate because people struggle to see a shape. In fact, if you look at the move along the horizontal axis, you will notice that the variance is increasing, but the measure we just introduced is clearly 0 because the ping points are flat. So this is clearly a variable which does something, but has a 0 sensitivity coefficient. And in fact, this is a variable which acts by a higher order coefficient. So the story is that you can decompose the variance according to terms of increasing dimensionality. Those of you who have studied design of experiment know this already. So you have two-way, three-way effects, so-called interaction effect. And all the terms are linked by the famous variance decomposition formula, the so-called ANOVA or Hofstadter decomposition. I mean, there are various definition of this formula, but in principle, you can have interaction effect up to the order k, which is a dimensionality of the problem. So the point is that almost nobody use a full variant decomposition in numerical experiment because the number of terms in a variant decomposition increase. They are of the order of 2 to the power of k, but even a second order terms, if you have 10 factor, the second order terms are 10 times 9 divided by 2, so it's already 45, which is already very many. Nobody wants to look at so many coefficients of sensitivity. So I'm just repeating in this slide what I just said, no? So people normally use something more compact as a measure, a single measure, which I can compute even if I don't know all these tens of interaction. And this is a measure called total sensitivity index, which collects for each factor the sum of all the interaction which include that factor. Of course, there is some redundancy here because T1 and T2 will share some terms, so this will no longer add to 1, but each T will give me the total influence of a factor. Okay, so you can also use this, and now I go back to the idea not to use a specific method for specific problem. I can tell you without much of a demonstration that if you want to identify a single most important factor because you want to maybe go out in the field and measure this factor better, you can use the first order effect. But if you want to simplify your model and to fix or eliminate factors, a group of factors, you have to use the total effect. Okay, then there is a lot of literature. I mean, people, in my club spend a lot of time studying methods to either new sensitivity measure or more efficient way to compute existing sensitivity measure. Here I showed two papers, one mine, one from Art. There is also a lot of software to do that. Available, you can easily find it. This is a recent addition on the Journal of Statistical Software by our team. We found very effective to work on model effective dimensions, which is also computed using sensitivity analysis. There are two ways to. Why are we interested in the effective dimension? Because the complexity of a model is not given by the number of variables, but by what those variables are doing. Normally, there are two definitions of effective dimension. One, truncation, which tells you how many variables are important. For instance, you have 10 variables, but only 3 are important. So this is the sensitivity, the effective dimension is 3 in this case. Superposition has to do with how many interaction of what order is the highest interaction term. So if your 10 factor have at most second order interaction, in this case, the effective dimension is 2. And those are the numbers which give you really how complex your model is. But we will go back to this in a moment. So we can say that those techniques are a kind of best practice, because they can be, graphic interpretation and statistical interpretation can be expressed in plain English. I haven't said that, but you can find it in the book. You can compute the sensitivity for groups of factors. I haven't shown that, but you can, again, read it in the book. We have seen that they can be related to settings such as factor fixing or factor prioritization, and then they give the effective dimension. And if you want, if you do the exercise in chapter 1 of this book, all these concepts will be put to a test. What is one consequence of this method being a best practice is that everyone developing a new method, here we have Razavi and Gupta, two people in the community of people crunching number and sensitivity analysis, they compare the performance of the new method against SI and TI. You can also use this method to do a sensitivity analysis of a sensitivity analysis. So this is a paper where we try to compete with two methods are put into competition depending on how many design parameters they need. So you can, this is interesting, but maybe this is not really what most useful for most practitioners. There are other methods, of course, which can be used. An important class of methods are the so-called model independent, because if your output Y is long-tailed, it doesn't make much sense to compute a variance there, so you have to use something else. And one is to look at how fixing a factor changes the entire distribution. These are so-called moment-independent methods. But there is also VARS, which is a kind of sensitivity coefficient which can be computed different steps, so that you can have full variogram across all the axes of each dependent variable. There are the Shapley coefficient, which can also be computed very efficiently and come more from game theory. I will not be saying much about this method. Only the problem is that if you look at the literature, most people do sensitivity analysis using changing one factor at a time, which is very intuitive, but is wrong. Okay, it's very intuitive because I say I change only one factor, I see a change. This is important for that factor. I'll try now to convince you that this is, though it is intuitive, it's not correct. Of course, this is evident for those who have studied experimental design, because in experimental design, you don't do that. You can change the parameter in combination. And this is the paper I'm referring to now. So I would say that if you change one factor at a time, what you do is a perfunctory sensitivity analysis. You go through the motion, but you don't do it. So here my demonstration, which is geometrical and everybody can understand it. If I move one step in from the center of this variable in one direction and then in other, I will be putting 2 points within this white circle, and I will never reach the gray corners. And the area of the circle divided area of square, you cannot answer me now, but I'll tell you that it's roughly 3/4. What am I trying to do? Well, bear with me. In 3 dimensions, the corners become mores, and in this case, the volume of the sphere divided by the volume of the cube is 1/2. It is going down. Now, in 10 dimensions, how many corners would be left out by this investigation? Actually, the volume of the sphere divided the volume of the hypercube in this case is 1/4 of 1%. So there are 99.75% of the input space which is unexplored. Okay, you can say, okay, but even the sphere is not terribly explored. Okay, but at least in the sphere I have a few points, but in 99.75% of the space I have nothing. So really this is in a sense surprising. It's a consequence of the course of dimensionality. This is how the point go down quickly with K. So this is really to explain that varying factor at a time is not useful. And additionally, you don't capture interaction, because interaction are only activated when you change more than one parameter at a time. There is this nice book written by Savage on to explain why the system are not linear. If I want to build a scaffold, like the one on the right-hand side, I cannot test the scaffold by shaking the ladders individually. I have to shake them when they are coupled. So this is a bit, how to explain in a visual way the idea of interaction. So then we did a review to try to understand why people keep using OAT, because this is what we see, and this is the paper where we, well, I don't do it now, but we have a number of reasons why people do this, and also to explain how this should be changed. Some people use also methods related to correlation or to regression, which are very good if your model is linear. We discussed this many years ago. The point why you should not use models which are based on assumption of linearity or assumptions of monotonicity is that before running the analysis, you don't know that. So if you knew in advance that your model is linear, you take a derivative and that's your sensitivity, or you take a regression coefficient. If all models are monotonic, you take a rank regression coefficient. But again, you cannot know this in advance. Well, many people will disagree with me, but many people like to use Latin hypercube sampling or optimize Latin hypercube sampling. I am sold to, I'm very partial to quasi-random sequences, and due to, in particular, I use LP-tau sequences from Ilya Sobol, which is shown here. Quasi-random sequences are not random at all. They are well-spaced, so-called well-spaced sequences. Art here is an expert on those sequences. There are a lot of things you can do with these sequences. For instance, they are used effectively in high-frequency trading, because this is where people have to integrate quickly Monte Carlo integral because everything runs into milliseconds. So you have faster convergence using quasi-random sequences than purely random point. So yes, stop here. What I wanted to say. Okay, this is a paper you find on Archive, which is a preprint server, but is very much quoted, where we have a demonstration of this comparing, Latin hypercube with random and with quasi-random. It was very, in the end, we could never publish this paper because there is a strong controversy on this kind of use of Latin hypercube versus quasi-random. Okay, so don't use the model just once. And it is something which is, may strike you as strange, but I say, imagine that you are building a model, and in the building of the model, you run the model. And normally, the way you do it, because I was a modeler a long time ago, is to run the model once. But this is, it happened to me pretty soon to understand that the best way to do this is not to run the model once, but to run the model a few times, 10, 20, 100, depends on how much you can afford, because there is a lot you can learn, especially at the stage of model building, by running the model over some kind of maybe little Monte Carlo. Because one thing which you do is you discover many more errors. The modelers joke about Lubarsky law of cybernetic entomology. There is always one more bug, and there is nothing like a Monte Carlo to make bugs jump out, because really you shake your model when you use some kind of model. And then furthermore, in my experience, when you take a model which is run in a kind of deterministic fashion and you propagate the uncertainty through it, you always have a lot of discovery. This is a recent paper, again, with my collaborators, and we discovered, for instance, that current model underestimate the need of water 50 years from now, future irrigated areas. This is an active line of investigation. We want really to show that that water or irrigated land, if you prefer, will be a problem much more than it is actually conceived by existing models and database. Here is another paper where we say that the accuracy which is given now by existing model is delusive. It does not correspond to what we can what we understand of the system. So these estimations are unduly precise, and this may lead to policy misjudgment, to the taking of bad, non-optimal policy, and this may affect many sustainable development goals. Here you need SDG 2, hunger, water stress, etc., etc. Okay, so one solution is the modeling of the modeling process. I'll try to explain this using some literature. Luis Borges, which some of you may love as a fiction writer from Argentina, he wrote this beautiful book, El Jardín de Senderos que se bifurcan, the Garden of the Forking Path, and it's a story of a Chinese author, which in his novel, in each chapter, it takes a piece of a previous chapter and change a bifurcation in the narrative. No, so the book is very confusing to read. One does not understand why a character which should be dead is instead still alive, because the book wants to run all the possible stories in all the possible ways. And so it's a kind of taking all the possible forking in a labyrinth. And you go left and then you go right. And the American statistician Yeomans has written a lot about that, talking about the Garden of Forking Path. In this case, he's referring not at the Chinese writer, but he's referring to the fact that statisticians do a lot of make a lot of choice when they select their design and perform their, for example, inference. And even when they are in good faith, so even when they are not trying to get a result in any possible way, doing something which is known as harking. Okay, but we cannot enter into all that. But it has to do with misuse of the p-test. They may, in fact, find an effect simply because they are changing the hypothesis which they want to test. So why this is important? Because actually this is what happens in practice. And when you try to to give to several statisticians the same data as in this particular experiment, you really find that there is what they call a hidden universe of uncertainty, no? So that in this case, the 71 different teams were given the same data to analyze, which were data on the effect of immigration on social policy. There was this hypothesis that countries with a robust flow of immigration had more restrictive social policy because they didn't want to distribute money to foreign people. And so 71 different teams tested the same data, because the research question was, will they find a similar result? Well, actually, they did not. The result, they are all over the place. They range from negative to positive in I would say, almost a dramatic way. You might find this discomforting, but this is what happens. No, this is really reality. In most time, people don't see that because you simply don't have 71 teams repeating the same experience. So you have this newspaper title like looking at the American flag favor people voting Republican, but all this kind of article, as people like Ioannidis and others have discovered, you know, they don't resist, you know, the test of some kind of exercise of this nature. Of course, when you do a sensitivity analysis, you shouldn't confuse the map of the territory with the territory. So again, here we could quote Borges, but no time. The sensitivity analysis informs you about what the model is doing, not the reality. And this is the point I made very clearly by Oren Pilkey in this fantastic little book, which shows how regular model used by regulator can be wrong. And he says, appunto, be careful that with the sensitivity in the model. If the model is wrong, your sensitivity is meaningless. The example he makes is the famous Yucca Mountain repository for nuclear waste. I mean, you know, the people in the US know this very well because every president changes, you know, the orientation on this repository. Works are open and close at every presidential election. But this system is described by a huge model called TSPA, Total System Performance Assessment, composed of really a lot of sub-models. And they assumed that the water will take a long time to penetrate from precipitation all the way to the repository level, which is some 300 meters below surface. Unfortunately, they discovered that the range of value they used for calculation was totally wrong for orders of magnitude. And they discovered this, ironically, because when they went and dug some holes all the way to the repository level, they found a trace of, do I say it here? Chlorine 36, no, I don't say. Well, they found a trace of radioisotope generated by the nuclear detonation back in the 80s. So they had to conclude that the water percolation was not of the order of the millimeters, but of the order of the meters. So a sensitivity analysis which moves from a wrong range of input value is really deceiving. And then there is this idea that you should apply one of the norm of kudos, no, of science ethics, one of which is organized skepticism. No, science should be communal, universal, disinterested, but also a scientist is first of all capable of being skeptical about her or his own result. So scientific mathematical modeling should involve a constant effort to falsify the model itself. Here we have, I'm quoting the late Steve Reiners, who talks about uncomfortable knowledge and the social construction of ignorance in policy discourse. And it's interesting that one of the 4 strategies which Reiner identified for dealing with uncomfortable knowledge is the so-called displacement, which is model-based. What is displacement? Displacement is when you look at what the model does instead of looking to what the system does. Okay, the model tells us that we are doing well, but this is the model. Actually, this is not what happens in reality. And the example used by Reiner is a Chesapeake Bay program, whereby they would look at the pollution of the lake, of the basin, not based on the measure in the field, but based on prediction based on the model. So this is interesting. There are other examples of bad modeling where the prediction of the model are manipulated to predict particular policy. More examples are in this other book edited by Sarevich, Pilke, and Ayerly. For instance, one case is one of model used for beach erosion, which was totally ineffective or totally unrealistic, if you prefer, because assumed some kind of normal way of consumption, erosion of beaches, while beaches don't follow this, they follow the behavior of extreme events, which are quite difficult to predict. Again, there is this other discussion that most modelers like to make their model larger because they want to capture more aspect of reality. I discussed this in this paper, short paper, and this is known as the conjecture of O'Neill. And the idea is that if you increase the complexity of your model, initially you do better because you improve your descriptive capacity, but then you do worse because you need to include more parameters, and this more parameter will carry more error. So this was discussed recently in this paper, which came out a few days ago on Science Advances. And we have shown, using again the concept of effective dimension, which we mentioned earlier, that if you increase the cardinality of the system, how many parameters are there and how many interactions are there, you have that the variance increase, the variance which you can take as a measure of the uncertainty in the estimate. Okay, so I'm repeating that. So this is also known as a Zadek principle of incompatibility by people doing, Zadek is a guy of fuzzy number theory. Precision and significance or relevance can become almost mutually exclusive characteristic. Mariia, I was discussing this with Mariia, who mentioned that, of course, when you do this, we must be sure that if we try to keep the model smaller, we should be sure that we are not skipping important variables. And this is a very good point, and I would say that if you do, but if you use effective dimension, you are doing a sensitivity analysis in a sense. So let's say, again, go back to the idea I was mentioning before. Now, always try to run your model in some kind of error propagation mindset, because then this analysis will accompany you in the process of doing all this, building the model, complexifying it, simplifying it, and procedure of this. So in a sense, you can, I show this again to say that you can try to sample everything, not just simply parameter or data, but also element epistemic. For instance, in a paper with Arnold Puy on irrigation, there are 5 different formulas for evapotranspiration of soils. Why using only one? Well, we take a trigger and we use this trigger to select one of the 5 at runtime. So, and this you can do for many, many different things, for many modeling assumptions. You can use trigger to activate those things, but you do this whilst everything else is also changing. So this is again the idea, everything is done simultaneously. So this is, I'm just repeating what I just said. Now you can sample even scenarios if you want. And I want to show this on a very simple test case. And this has to do with building a very stupid model, a composite indicator, where you can change the number of indicators, you can change the way you do the weight, you can change how you aggregate the variable. Normally it's done additive, but there are also multi-criteria based method or multiplicative, as in the Human Development Index. And I show you how this works. Also the missing data, you can decide what strategy, what system you use for imputation. And if you make a choice for each of these different things using the triggers, as I mentioned before, you can have different results to compare, in this case, different countries. And so you can now say with some robustness that countries 1 and 2 are similar, while country 3 is different. And well, I also recommend don't go public with your result without having seen your sensitivity analysis. And I will show you an example of why this is not terribly useful. This was a few years ago. There was this controversy over the cost of climate change. Those are two scholars. Nordhaus is kind of, you know, not convinced that we should invest much to fight climate change because the damage is moderated, and Nicholas Stern is on the other side. And Nordhaus criticized Stern on the basis that he used a different discount rate, which is one of the parameters which enter into a cost-benefit analysis of the effect of climate change. So a posteriori, Nicholas Stern did the sensitivity analysis to show that his results were difficult. Now, what you see here is the result from Stern. I believe that this is meaningless. For me, people calculating whatever happened in the economy 2 centuries from that now are simply, you know, I don't know, I don't want to use bad words, but I don't believe in any of that. But just for the sake of the analysis, what I see in this plot, and there is indeed a lot of uncertainty. So it is true that there is an effect, but the uncertainty is also very, very large. So if I reverse engineer what Stern has done, I see that there is indeed a large uncertainty. So I believe that neither of them, neither Stern, neither Nordhaus, can usefully say something meaningful about what will happen in terms to the economy as a result of climate change. Really is a calculation which is, I know that many people do it and many serious people do it, but I don't agree with what they do because they are, you know, precisely wrong, as Keynes would have said. Okay, so I think I would, I think I have a few slides, then I stop. This idea of using sensitivity analysis to confess your uncertainty is also popular among econometricians. Here is the late Peter Kennedy. You should confess in the presence of sensitivity in order to anticipate criticism. And then maybe my last recommendation, and I would, and this is the one where people makes more, how shall I say, people don't understand easily this point because they say, what is wrong in changing all the factors by the same amount, 5%, 10%, or 20%? I believe this is totally wrong because when you do a sensitivity analysis, the most important part is really the uncertainty in each parameter. This is what adds value to your analysis. If you give to all parameters the same uncertainty, means that you are equally uncertain on all of them. This is an example of where it was done, and this really, you know, doesn't mean anything. I mean, you know, I don't know how to put it, because in this kind of pandemic model, there are parameters very different in nature, which are, of course, affected by different ranges of uncertainty. So in fact, some people say that when you do one analysis of sensitivity, the most expensive part of the analysis is to derive those coefficients. I think I will stop here. There are a few more slides. No, it's finished here. This is the end of my presentation. If you want, you can read this paper, and where some of these things are also discussed. But okay, I'll stop it here so we can have some questions.
Andreas, thank you so much. It's such a thought-provoking presentation you have here. Yes, we have some questions. Art, please go ahead.
Oh, I was just putting up an applause, but
Okay.
I'll have a comment though. I think there's a notion of mean dimension, which can be easier to use than effective dimension. If you just add up the total Sobel indices, if that adds up to something, you know, a little bit, just a little bit more than 1, then you know the function is very additive. And estimating the effective dimension can actually be kind of tricky.
Yes, but if you compute a global sensitivity analysis, you can compute the effective dimension. Why you say I cannot do that?
Well, the mean dimension depends only on total sensitivity indices. The effective dimension may involve knowing lots about all the 2 and 3 factor interactions and or the k factor interactions. And so those are more expensive to find.
Yeah, but if you compute the total sensitivity indices, you get a good handle, as in the paper we just published.
Yeah.
This is the way we do it. Yeah.
Yeah. Okay.
Yes, that's actually about effective dimensions and about your last paper from Science Advances. It's such a counterintuitive, right? Indeed, people around the world in many different industries, they try to make their models more realistic, more precise, and yet you're showing that it's actually harms more often than helps the situation.
Not always. I mean,
not always.
Let's be clear. If you are in machine learning and you have zillions of data, this may not be true at all.
Absolutely.
I'm only talking of those cases where you are trying to put points in a region of space or time where you don't have data evidence. Okay.
Yes.
And then, okay, we can open the discussion on hint casting. No, my model is good because if I do hint casting, I can predict the present. But again, other philosophical discussion, will the future be like the present? So mine is not a general statement, it's rather more a statement about models we try to predict into the unknown, okay? So which are often used in policy, like the cost, the social cost of carbon is a classical example. Now people spend a lot of energy calculating the social cost of carbon average over the next 3 centuries. I'm not kidding, that's official estimate for the USA. And I believe this really, you know, those numbers which are given with 2 or 3 digits are fantastic in a sense.
Yeah.
No? They're fantastic. Yeah, I call them fantastic numbers.
True. Julian, please go ahead.
Okay, suppose I've got a model. I've constructed a model, and I'm really a naive researcher. I'm not sure how to approach analysis and so on. You talk about a false sensitivity analysis. How should one approach an analysis to make it a true sensitivity analysis, given that you've constructed a model? What would you view as the steps to make it a true sensitivity analysis?
Well, if you do scatter plots, I'm happy. No, if you do your modeling work and then you show me the scatter plot of each and every variable with respect to the output, I'm satisfied, because then, you know, if there is something going on, you can see it there, and this is very easy to do. You can do this with a spreadsheet Excel, but then you are global. But in order to do that, you still have to change all the parameters simultaneously. This would make me, you know, satisfied.
How about if you were trying to publish that, though, that sort of study? I mean, I think at the publication level, they would want more. They wouldn't be satisfied with the scatter plot. They'd want you to be digging into that.
Well, then you compute the variance of the scatter plot, and you have computed the variance measure, or you can use a different method. But as I say, like a moment independent or a Shapley coefficient. But again, I would encourage you to explain to the reviewer in this case why you have selected this particular method. Or because this is a context where there can be different groups of variables, because each variable represents each simulation represents one particular team. Then the Shapley coefficient, which come from game theory, are more appropriate. For instance, for a composite indicator, Shapley would be considered an intelligent choice, you know, to make. But again, or would you say, no, I use this method because I want to simplify the model, and then I use total sensitivity coefficient. Again, or my model, my output is very long tail, so I could not use other method. I had to use some method based on the full distribution of the output. I don't know. My friend Saman would say, Rajavi would say, if you suspect that there are local features you want to capture, use variogram methods. I don't know. There are different possibilities to choose from.
Yeah, but as long as it's not one at a time analysis, then
provided it's not one at a
time.
No,
yes.
This is perfunctory. Yeah, this is what I define perfunctory, because you don't activate interactions.
Yeah.
So either you are very lucky and the system is linear, or if you are, but systems are not, I mean, especially modeled in ecology, they are mostly the solution of system of differential equation. They always include exponential, and the exponent is itself a function of something else. These systems are almost never linear, let alone, and probably not even additive.
How would you capture the, I'm coming back to this scatter plot idea. How do you cut through the multidimensionality aspects, though, to construct scatter plots that would satisfy the true nature of it?
Well, the multidimensionality, you put it in yourself. No, you put it into the cylinder to start with, because you are the one who selecting rows, sample matrix, and selecting rows of parameter values and plugging them into the model. So it is you who put the multidimensionality into the analysis. And the scatter plot gives it back to you, because you can see, for instance, when the variance of the output changes moving along the x-axis, this is could be as a symptom, for instance, of interactions. And with a bit of practice, you learn how to see this. Okay, but surely you see which factor is doing something and which factor is doing nothing, because when you see a cloud of points filling the scatter plot, this factor is doing nothing.
Yeah, Andrea, how about this one factor at a time analysis? Indeed, there are so many scholars and using it, and it's used so much in industry as well. Why people not using proper methods that include interactions?
Because it needs a bit more of statistical, patience to set up the analysis globally. And also there is a very practical problem that when you change all the parameters and the model crashes, you don't know why. Okay, if you change only one and the model breaks, you know that that parameter is doing something which you don't understand. But if you, it takes more, it's more laborious to do this globally, because then you don't know what happened when the model goes down.
Yeah.
This is one of the reasons, which is a good reason, but I understand the problem, but
Another good thing you mentioned in that paper about this topic is that at least for finance people, perhaps that's true, that when you vary one factor at a time, then you're within nice limits of
ranges,
ranges of the output. Yes, but when you vary all together everything, then you suddenly see very scary numbers on your graphs.
Exactly. In this case, there is a kind of political economy of mathematical modeling, and then the game becomes, what can I get away with? So this is a bit cynical, but this is also part of the world we live in. The people doing the calculation for the bundled mortgage, which were at the root of the crisis of 2008-2009, the so-called quants, econometrician crunching number to compute the pricing of those exotic products. They were playing with fires, and they knew that. I mean, in hindsight, we know that they knew. And that they were playing with fire, but they were making a lot of money. So in this case, they had really an incentive to downplay the risk.
Art is asking, do you have a preferred method for handling dependent input variables?
For handling?
Dependent correlations.
Dependent. To be honest, I'm not a big fan of handling correlation. I never published a single paper in my life about this, but many of my colleagues do. I know it's a very active field of research, but I could never put my heart to it because I believe there is, if people don't do it with normal parameter, I should be given a test case where I really have to do it, but it never happened to me. So I'm not an expert to answer this question.
Mm-hmm. So the compelling case is when there are constraints on the variables and it's not even a cubical region.
Exactly.
So then they have to do something, but it's very hard to find one of those somethings.
Mm-hmm. Oh, no, I agree. You're right. You're perfectly right. I know that, as I say, most of my colleagues and friends like to work in this field and to work when you have boundaries. No, you cannot sample in the hypercube, but you have to sample in regions of the hypercube because some surgeons are forbidden. Huh?
Yeah.
As I said, I never had a case which pushed me into doing this. Maybe before I die.
But art is what you're teaching in your lectures, right? That everybody feels pain when dealing with correlations.
Oh, yes.
Yes.
Well, yeah, dependence is even worse than interactions.
Yeah. What is your preferred method to deal with them? Is it Shapley?
So I've been looking at Shapley methods and they lead you into some difficulties, but I think you're destined to get difficulties when you try that. So at the moment, Shapley is my favorite, but I would like to find something better, or maybe find a way to do Shapley easier.
Mm-hmm. Yeah, we are now. Sorry.
No, and then in machine learning problems, this just explodes in complexity, because now they want to explain not just the variance, they want to explain one single decision. Why did this person not get a loan? Like there's no. It's hard to even think what distribution you should put in. So it's not quite global sensitivity analysis, but it's
yes.
It's related, and the issues of thinking what you should do seem really hard.
Yeah. Bertrand Yost is publishing a chapter in a book where it tackled this issue, and this is a field where I work a lot now on algorithmic transparency.
Okay.
This is the study of the protected attribute. No, normally they say that the algorithm is not racist because it does not include the color of your skin, but the color of your skin is implied by the other variables which are in the algorithm, because where you live, what school you go gives away this kind of information. So if you use sensitivity analysis, you can discover this racist algorithm in a sense, which pretend not to use this protected attribute, but in fact do use them.
Yes, I've heard also that sensitivity analysis is very nice for detecting some anomalies in machine learning trained networks, like, for example, models. For example, if somebody trains the visual such that with the red glasses, the model doesn't recognize you as a human being, and so doesn't try to identify your face. So these kind of things can be spotted as well. Yeah.
There is a fantastic movie, a documentary on Netflix done very, very well on this, called Coded Bias, if you have a chance. Coded Bias. And they're doing a very good work at there is another one which is also fantastic. It's called The Social Dilemma on the use of big data and cognitive psychology to influence voters and consumers, which is also very, very good. I mean, this interesting work is being done in this kind of field, like documenting, using documentary, visual aid to this kind of complex problem, which I wouldn't believe that this could be done in a sense, because normally you had to read a bunch of books to understand what's going on in those domains. But people into the media world, they can make pretty good work at showing it in a compact form, 40, 50 minutes of movie, and give you really what's going on in a very clear terms, interviewing precisely the author of these books, which you otherwise would have to read.
Yeah, have to watch now. Thank you for recommendation.
Yeah.
Yes, I believe that we can do easily another hour or two of discussion with this company, but we must let you go, Andrea, right?
Yeah, thank you. No, it's okay. You can email me, and you have my slides online, so I
Yes.
can send it to you if you want. And nice to have seen you.
Yeah.
And
Thanks for coming.
let's
Thank
be
you
in
a lot,
touch
Andrea.
and think of something to do together, maybe.
Absolutely. Absolutely.
Okay.
Thank you, everybody, for joining.
Goodbye.
Bye.
Ciao, ciao.